Hi there, Mr. Sutton here, bringing you the Pre-Cal Honors 4-1 Extra Practice Number 2 solutions on exponential functions. On this problem, we need to graph this exponential function. So let's start by making a table, and for x values, we get to choose them. I'm going to choose the x values -1 through +2. So plug in all those in. We've got 1/4 times 4 to the -1. Well, that's really 1/4 times 1/4 because negative means reciprocal. So that's 1/16. And then if we plug in the 0 power, that's 1/4 times 4 to the 0, or just 1/4 times 1, which is 1/4. And you can see we're multiplying by 4 each time. So this next one is just going to be 4 times 1/4, which is just 1. And 4 times that's going to give us 4. So plugging all those into the graph here, we've got -1, 1/16 right there, and then 0, 1/4, 1, 1, and then 2, 4. And then just drawing a curve that has a horizontal asymptote. There we go. So there's our exponential function. In order to graph this one, let's make a table. So I'm going to use the x values -1 through +2. Plug in all those exponents in. I've got 2 times 3 to the -1. That's 2 times 1/3, which is 2/3. After that, we have 2 times 3 to the 0, which is just 2 times 1, so 2. And then 2 times 3 to the 1, 2 times 3 really is 6. And we're just multiplying by 3 each time, so this next one then, one way or another, is going to be 18. So I've got -1, 2/3 somewhere over here. And then 0, 2. 1, 6 is all the way up here, and then finally we've got 2, 18, which is all the way up here. So this exponential function is growing pretty quickly. Don't forget the horizontal asymptote as you move to the left here. So there is our exponential function. On this problem, we have an opera house which is selling 14,000 tickets this year, but it's been dropping 5% in ticket sales from one year to the next. If this keeps going on the way it is, how many tickets will they sell 7 years from now? So we have a percentage drop every year. So this is an exponential decay function. And since it's happening every single year, we can use the standard exponential model, AB to the t. So in terms of plugging things in here, for the t value, the input, we've got the 7 years, because we want to know what the sales are going to be 7 years from now. So f of 7 is what we're looking for. A value, that's the initial amount. That's going to be the 14,000 tickets. For the B value, this is what we're multiplying by every year. Since you're losing 5% every year, we've got 1 minus 0.05 is 0.95 for the decay factor. And then for the exponent, the t value, that's just this 7 over here. So let's go ahead and plug all of that into the calculator now. So plugging all that in, let's see what we end up with. It looks like that's going to be 9,777 tickets if we round up. On this problem, we have a town with a population of 1,000, and that population is doubling every 5 years. We want to know what the population is going to be 15 years from now. So in terms of exponential functions, we can use the half-life formula here because there's a wait period before we're allowed to double. So we can use AB to the t over k for this one. I'm going to be doing f of 15 because that's the time period I want to figure out more information about. For my a value, that's my starting value of 1,000. And then the b value, what I'm multiplying by each time, that's going to be 2 because we're doubling. For the t value up here, we've got the 15 that we just plugged in. And for the k value, that's how long we have to wait. So that's this 5 years over here. So 15 divided by 5. And now let's do that on the calculator. Although, come to think of it, we don't really need the calculator here. I mean, 15 divided by 5 is 3. 2 to the 3rd is 8. 8 times 1,000 is 8,000. So that's going to be 8,000 people that are in that town 15 years from now. On this problem, we have Mitch culturing bacteria that have a growth rate of 15% per hour. If the current population is 21,000, how many bacteria will there be in 17 hours? So since this happens every hour, we can use the standard exponential model. We don't need the half-life formula here. So we can go with AB to the t. So we're doing f of 17. That's the time unit we're trying to plug in here. For A, we've got the starting amount of bacteria, which is 21,000. For B, the growth factor, we're growing 15% per hour. So we're multiplying by 1.15. And then for the t, we're plugging in the 17 there. So now it's time for the calculator. So here we go, plugging all this into the calculator. And it looks like that's going to come out to, wow, 225,987 bacteria if we round off. 86. Let's round that up to 87. There we go. On this problem, we have Yoshi with $7 in a savings account. I'm not even sure if they let you open one with only $7, but hey, let's allow it. The interest rate is 10%, compounded annually. To the nearest cent, how much will his account grow to in 13 years? Since we're growing once a year, we can use the standard exponential model, AB to the t. So we're going to be doing f of 13. That's what we're plugging in as our input on the time. For the a value, that's his starting amount, his principal. That's going to be 7. For the b value, that's what we have to multiply by every year. Since we're growing 10% a year, we're multiplying by 1.1. And then for the t value, the exponent, that's going to be this 13 right here. So let's figure this one out on the calculator. All right, here we go, calculator time. Let's see what Yoshi's money's turning into. And it looks like he's going to end up with $24.17. Don't spend it all in one place, Yoshi. On this one, due to inflation, a fixed quantity of money can buy 5% less every year, so the purchasing power is going down. If Billy's got enough in his wallet to buy 31 movie tickets right now, how many movie tickets could the same amount of money buy in 19 years? So since we're going down 5% every single year, we can use the standard exponential model. There's no waiting period here, so we just have AB to the t. We're doing f of 19. That's the time we're inputting here. For the a value, we're starting with 31 movie tickets that we can buy right now. And we're going to multiply that by, let's see, if we're going down 5%, that's going to be 1 minus 0.05, so 0.95. And then for my exponent here, my t value, that again is going to be 19. So let's use the calculator at this point. All right, here we go. Let's see how much that money can buy. It looks like about 12 movie tickets if we round that off. On this problem, we have a town with a population of 5,000 that doubles in size every 70 years. We want to know the population 280 years from now. So since we're doubling every so often, we're going to use the half-life formula, AB to the t over k. And we're going to be plugging in 280 for the t value here. For the a value, that's the population we're starting with, so that's 5,000. B value, we're doubling, so that's going to be times 2. T we said was 280. K, that's how long we have to wait before the doubling happens, so that's going to be 70 years. And we could do this on the calculator, but we know 280 divided by 70 is just 4. 2 to the 4th is 16. So we've got 5,000 times 16. Well, 5 times 16 itself is 80. Stick on 3 zeros, you've got 80,000 people. On this problem, we have a private school charging $51,000. Now, this problem was written, that was considered cheap, but maybe not so much anymore. This figure is expected to rise 5% each year. What'll the tuition be in 9 years? Okay. So we're going up 5% every year, so we can use the standard exponential model because there's no wait time for multiplying by the growth factor. We have f of 9, that's our input for time. A is this 51,000 that the tuition currently is. For B, every year we're multiplying by 1.05 because we're going up 5%. And then for the exponent, we've got 9. So let's use the calculator for this one. So it's looking like that's going to come out to, drum roll please. Well, didn't want to add a 3 there. We just want 9 years, not 93. That's going to be $79,117.74. Time to start saving up.